So I'm gonna talk about two projects. One was a soda paper, and one is an ongoing work, which should be out very soon. But right now, there's nothing online to see as of yet. And I'll just comment. Steve pointed out to me that Mortez is no longer at Charles. He's somewhere else, but he's been moving around. Okay, so he's half at Charles, but not physically there right now, at least. Okay, so everything that I talk about is going to apply to a range of clustering problems, but just for kind of ease of exposition, I'm going to talk about k-median, and most of the things will generalize further. So just for the notation we're using, D is going to be my metric all the time, except I guess I'll use it later for dimension. And then so S is going to be the set I want to cluster, so I get some multi-set from my metric space. And then given any set of centers, I'm going to define the cost of that clustering as just if you want to look at this picture here, if I want to cluster all these points, and you ignore the colors for a moment, and you see that there's these 4 stars. So if that's my center set C, the cost is just I draw a line from each point to its center, and I just add up the distances of all those lines. So it's basically just the sum of all my connection costs. So that's going to be the cost of the clustering. And for OPT of some set, K is just the minimal cost that's possible for any center set of size K. So here you see S is my points, my centers are the stars, and here K is 4. I've used 4 different clusters. And in general, we won't be able to find a center set that actually achieves the optimum. So we'll just have an alpha approximation where the alpha is how close I come to the optimum. So I'm going to overshoot the optimum by no more than a factor of alpha. Okay, so the related problems, one is k-means, where I just, instead of taking the sum of the distances, I take the sum of the distances squared. And more generally, M estimators, where, so for k-median, I just took the sum of the distances. For k-means, I squared that. And in general, I can just take any function of the distance. And our techniques aren't going to work for just any function, but there's some kind of modest requirements, like a triangle inequality and this log Lipschitz condition. But the pretty basically, all the kind of regular nice functions are going to fall into, this is going to apply to all of those. So one typical example of this is a Cauchy estimator. So basically, it kind of drops off as log as you go to infinity. So if you want to cluster, and it might be more robust to outliers to kind of change the objective function that we're trying to minimize. So so we can talk about the metric case and the Euclidean case, and obviously the Euclidean is just a special case of the metric. So all of the algorithms for metric will apply for Euclidean, and all the lower bounds for Euclidean will apply for metric. So for Euclidean, it's NP hard, but we have p tests for this. But for the metric case, it's max S NP hard, and the hardness is at least about 1.735 under this assumption.
The 1.735 is not correct. It assumes the facilities set is different from the demand set.
I see. So if you
force them to be the same, that exact reduction does not work.
Oh, really? Okay. So I didn't.
Instead of 1 plus 2 will be, so we only 1 plus 1 will be.
Okay. So like 1.3 or 4, like this. Okay. Okay. Thank you.
So that's for when the facility set is disjoint from the demand set.
Mm-hmm. Okay, thank you. Yeah, okay. Okay, so I guess for the case that we'll be doing, they're going to keep the facility set and the demand set the same. So basically the centers, for the metric case, we're picking centers which are from, we're picking C, which is not only a subset of the metric space, but a subset of our input S that we're clustering. So in this case, as was just pointed out, this is actually going to be lower, like 1 plus 1 over E. And in terms of upper bounds, the best offline approximation is like 2.6, which was just last year. Okay, so we're going to be working in streaming. So in advance, someone gives us k, how many clusters they want, and n, the size of the input. And we can, there's just some kind of easy tricks to get around knowing n in advance. So really the thing is that we know k in advance, and we get a stream of data. So the points are arriving one by one. And we want to maintain a clustering using sublinear memory and hopefully polylog memory. So polynomial in k and some polylog in n. Okay. So all of the solutions for these clustering problems have kind of fallen into two categories so far. And all of them kind of have this same workflow where they get the input set and they kind of reduce this into some small summary of the data. And then at the end, if you actually want to query for a solution, it just says run an offline approximation on your summary. So all of the algorithms kind of have this two-step. The whole innovation in the streaming algorithms is this arrow here. When you get your stream, how do you create the summary? And then at the end, it just use the black box, whatever the best offline approximation to actually get your centers. But this first arrow comes in two flavors, and one is kind of an earth mover distance, and one is core set. So I'll just explain what these are. So for earth mover, so if I have two multisets A and B, the earth mover distance between them is basically these are like, these can be, you can think of them as weighted points, a set of weighted points, and I just kind of, if I have two sets, I want to say if I want to have a set A and set B, and they have to have equal weights, how much weight times distance do I need to kind of push A around to turn it into B? So more formally, if I just take a bijective map from A to B, I just sum over all those distances. So the way that all these work is they maintain a set, this summary, such that the earth mover distance is bounded by some constant times OPT. And running an offline approximation on that, they get this also some constant factor approximation on the original set. So the crucial part is this is the guarantee that all these algorithms have, that the earth mover distance, which is just kind of connecting the original stream to your summary, is some constant times OPT. So kind of in terms of like facility location, you can think I have n points originally, and maybe I can find some log n points where I can connect these n points to this small number of log n points, and the sum of all those distances is some constant times OPT. And if that's true, I can get a constant approximation on the stream, the original stream, just by running a constant approximation on this facility set. So the pro of this is low space, it's k log n, which there's no proof that this is optimal, so it might not be, but it kind of seems reasonable that you might expect it to be optimal. And the con here is you get a large approximation factor. So you can see this is the factor. This factor of 2 there is coming from the fact that you might, these offline approximations, for general metric spaces, you give it this set P, and it clusters P using centers from P. But it might be possible that if you use centers outside of P, you can drop by a factor of 2 the cost. So without having that flexibility, we get the factor of 2. But all in all, alpha has to be greater than 2. There's a really simple lower bound for that. So even if you run a brute force solution, trying an exponential time, find the perfect solution on P, you're never going to beat an 8 approximation for the original stream. And even more so if you run a polynomial time algorithm, you won't be better than 17. And the best result is due to Guha and some other authors, and it's a 34 approximation. So there's low space, but you're suffering on approximation factor. The other type, a core set, is we find a set P that arbitrarily closely approximates the cost. So we can get a very good approximation factor. Again, the 2 is coming from the same reason that you can't use the centers, but that you might use you can't use centers from outside of your input set. But in general, this is, you can make this arbitrarily small. So if you had infinite time and you literally tried all the centers in your metric space, you can have an arbitrarily low approximation factor. And in polynomial time, it's 5.33 using last year's offline approximation. So the con here is the best known is this log to the 4th for metric. So this is a con versus just the log n. We have log to the 4th. And for Euclidean, there's several results, which are now. For Euclidean, this is kind of the history of the Euclidean core sets. And I think so these are all for streaming. And all of these papers, including the metric case papers, they write an offline core set. So for this one, it's k e to the epsilon to the d log n with just a single log n. And then when they move to streaming, they incur all of these extra factors of log n. And same for this one. This one is actually completely independent of n. They get a core set of k squared epsilon to the d. That's it. And then when they push to streaming, they get all these log n factors. So same with Chen here, it's log squared n in the offline. And Feldman and Lamberg is independent of n. But then you push to streaming and you get these log n's. So the same thing happens here. Yeah, they can. Right, and the third as well, actually. So in general, if you have an offline core set that depends on epsilon, like epsilon to the negative x, just using the merge and reduce technique, you can get a streaming core set with a multiplicative factor of log to the x plus 1 n. So for this one, if you wanted to, you could get log to the d plus 2 instead of log to the 2d plus 2. And for Chen, he can get he's log squared, so he could get log to the 5th instead of log to the 8th. The only one that's optimized, he actually uses the best you can possibly do with the merge and reduce technique. So is that what you were saying?
I think you can get even log to the constant over the I'm not entirely sure.
For the final core set or for the space needed during the construction?
Like if you have epsilon to the minus d, I think we get a log to the d.
Log to the d. Without plus 1?
Yeah.
Okay. I'm actually going to go through merge and reduce, so maybe you can point it out if you see how to do that. Okay, so for kind of, this is the technique that we were talking about. These Feldman and Lamberg, they have, in general, core set of epsilon to the negative 2 times this VC dimension of the problem, which this is, there's another thing, sensitivity, which they define, which I'm not mentioning. So this statement is not quite true, but for this specific case, they prove the sensitivity for these problems is constant. So it's true in this case, at least. So they show the VC dimension for Euclidean k median is dk, and for metric k median is k log n. So they get, so in general for metric k median, they have 1 over epsilon squared k log n. So using just the merge and reduce technique, they incur an overhead. You just take the exponent on the epsilon and then add 1. So this incurs an overhead of log cubed. So what's the time? It ends at 4:30, right? Yeah. It started at 3:40. Well, I won't go past the 4. So merge and reduce technique. So just kind of overview of how it works. Let the bottom be your stream. So this set of rectangles is your stream, and you're going to accept the stream in chunks. So let this pick some constant m that is big enough to fit in memory, or small enough to fit in memory, and take the first chunk m, and this tree is going to be, each node is going to be a core set, okay? And so first of all, this whole technique is based just on the following 2 observations. If you have 2 k epsilon core sets, So what's a core set? I'm just saying when I evaluate, see it's when I evaluate the cost on my core set P, which is the core set, it is basically an epsilon approximation for the cost on the core set S, for no matter what the centers are. So if I have one core set and I have another core set, and I just take the union, they're going to be a core set for their union because each of them is individually an epsilon approximation. So that works. And additionally, if I have an original set and I take a core set of that, and then I take a core set of the core set, I compound this construction twice. I basically add them plus a lower order term. Okay, so based on these two properties, let me take the first chunk and build a core set, take the second chunk and build a core set, and now let me take basically whenever I have two child nodes that are full, compound the core set construction to reduce them to a single core set. So here I'm going to have one kind of depth 1 core set here. And I do the same thing. Now the two child nodes are full. Compound it. And now again I have two child nodes that are full, so I move up. And I do the same thing here. And it goes all the way up until I've finished my stream and I just have one core set remaining. So how do we make this work? Each time I have a loss, an approximation. So if I want to have a k epsilon core set at the end of my stream, each one, what's the depth of this tree? It's going to be log n. So each one of my core set constructions I should actually build an epsilon over log n core set, so that when I come a little bit lower, like epsilon over 2 log n or something, because of just the lower order term. But essentially epsilon over order of log n. So in order to be right at the end. And then in addition, at the worst possible moment, there can be one core set per level. So the depth of the tree is log n. So again, each space, it's going to have a higher order a factor because I used epsilon over log n. And then also there's going to be log n of them. So in particular for his, it depends like 1 over epsilon squared. So I'm going to get a log n squared for accuracy, and then I'm going to get a log n because I'll keep log n of them at the worst time. So again, it's going to be log cubed n at the end, plus times whatever his offline core set size is. Okay, so here's that. The metric case, it becomes streaming, and then Euclidean becomes streaming again, all times log cubed n. So basically our new results for this is that we have a new technique. The first technique for, at least for metric case, that is not merge and reduce. Previously this is the only technique for building the metric core set. So we reduce overhead to O1. So here we have a metric streaming core set of his offline size, so epsilon to the negative 2k log n. And this will work for the metric case at least, and we're trying to make it work for the Euclidean, but no success yet. So number 2 is done. Number 3 is hopeful. Not yet a result, but hopefully soon. And these generalize to these M estimators. And as a separate result, we have a k. His result was specifically for k median, and he couldn't use an approximate triangle inequality. So we've improved this for a new core set that's linear in k, even for k means. So this would be the first that's linear in k. Okay, so I'm just something should be posted in the next month at least, but nothing online yet. So just to kind of say what the result is for now. So now I'm going to talk about the SOTA result. It's for the sliding windows model. So here the data arrives in the same way as the previous streaming, but we're only interested in computing the clustering for the most recent n elements. So our set S that we want to cluster, every time we get a point, in the old model we just added a point to our set of interest, but here we add a point and we implicitly delete the oldest point, so one point gets removed. So the thing that makes this model hard is the deletions are implicit. So for example, imagine sum of integers. So if you have some sum which is currently like 1,000,000, and you get a new point which is 10, so you add it, you get 1,010,010. Well, what point do you delete from your sum? You're not told that. It's just the last point, which using sublinear memory you've probably forgotten. So this becomes challenging. So problems like maximum in the worst case, you might need linear memory if you have a decreasing sequence. So these become hard. So this is strict, at least when your window size can change, this is strictly harder than the insertion-only model. So for this model, for known results, there was nothing that was noted for Euclidean, but actually there's this insertion-deletion core set. If you use a heavy hitters algorithm, you should get some poly k-log space core set. And for metric, the only result is a polynomial space, kind of arbitrarily low polynomial space, but still polynomial, constant approximation. And these authors, this is from 2003, and they posed this open problem. Can you get a polylog space? So our two results here are a polylog space framework that you kind of put in as not entirely as a black box, but basically all the known insertion-only constructions work with this, and it will give you a sliding windows result with well, I'll show the space bound on the next slide, but you kind of square the space times log n. And then we give the first polylog solution for the sliding windows model in metric. So this is with Vladimir Braverman, Keith Levin, and Morteza Monemizadeh. So we gave input an order of S space algorithm. This is for the Euclidean case. Just input this algorithm with S space, and we get a sliding windows algorithm in this space. And we didn't have time before the deadline to kind of go through the proof for the KJ subspace, but everything seems there doesn't seem to be any problem to generalize this, so it expected to work for the KJ subspace problem as well. And for the metric case, we give a constant approximation with k to the cubed log to the 6th n space. And this also holds for k-means. It holds, all you need is the approximate triangle inequality. So it will work for anything that satisfies some approximate triangle inequality, such as k-means. So previously, a major technique for converting these insertion-only algorithms to the sliding windows is smooth histograms. So how this works is smooth histograms is you take a smooth function, which is a function which satisfies this condition, and so the condition is basically if I have two sets which have a similar cost. So I have some non-negative monotonic function f. So in our case, f is going to be the OPT. So OPT you can consider as a non-negative monotonic function because OPT is always non-negative. It's the cost, the minimum cost. And it's monotonic in the sense that if I have one set and then a superset of that, the OPT of the bigger set will always be bigger than OPT of the smaller set. So it has to satisfy this condition. If I basically have a prefix and a suffix such that f, again, this is monotonic, so f of b is always less than f of a union b. That's always true. But in addition, if it's not too far less, if I multiply it by alpha and it becomes bigger, so basically, the prefix and the suffix have similar cost, then adding any suffix onto those, it remains similar to some constant. So for example, sum is a smooth function if I sum integers. So if I have, let's say, a be like the first 100 integers and their sum is 1,000, and then b is like the next 100 integers and their sum is only 100. So here I can say, okay, 1,000, what did I say, 1,000 and 100? So 1,000 plus 100 is less than, let's say, 2 times just 100. Or let this be the 1,000, sorry. Let b be big. So let's say 100 and 1,000 is less than like 2 times 1,000. So no matter what I add on, they'll always stay within a factor of 2. So even if I add on, you know, 1,000,000, it's still going to be like 1,000,000 and 1,000 versus 1,000,000 and 1,000 and 100. So basically, things that are similar at some point always remain similar in their cost. So sum satisfies this, LP norms, the frequency moments, lots of problems, but not the k-median clustering, which necessitates the need for a new technique, because we can't just blindly apply these smooth histograms. So it's kind of easy to see why they're not smooth. So this is an example for the k equals 2 case, and I think it should be pretty clear that this generalizes. So let A just be this kind of tight cluster of points, and B be this tight cluster. So here you can see for k equals 2, I can put a center here and a center here, and the cost is pretty low. Okay, make the cost arbitrarily low as you want by just making the cluster tighter. And then also this B itself is pretty low. I can just put 2 clusters there. So together, these are both very low cost things. As a matter of fact, I could actually collapse them all to a single point, and you'll see both these numbers are 0. Okay, so the condition is satisfied. But now, if I add this suffix C, all of a sudden, B union C, I can put 1 cluster there and 1 cluster there. So small OPT. But all of a sudden, when I try to all 3, one of these clusters has to make this huge jump to the other ones. So this OPT blows up to arbitrarily big. I can separate the clusters as much as I want. So no matter what alpha and beta I pick, the clustering doesn't satisfy the smoothness condition. So here's the condition it doesn't satisfy. But adding one more hypothesis, we can get the same result that we want at the end by just requiring one more thing. So here, the first condition is exactly the same as the smoothness, and the result is the same. So the only thing that's changed, as I said, in addition to the costs being similar, there also exists some clustering such that the cluster sizes of A are less than the cluster sizes of B. So by a B approximate clustering, I mean of A union B. So take A union B, find some B approximate clustering, so some clustering which is B times OPT in its cost. And once I have this clustering, I can ask for each center, so take the ith center, I can say how many points of A are connected to it, and how many points of B are connected to it. And if the number of points of A connected to that are less than the number of points B connected to that, if that holds for all of the centers, then we can actually say that no matter what suffix comes after, they will always remain similar in OPT. So this is, the proof is basically for one median, and for k median, you just kind of keep track of which are in which clusters. But this is the main idea, and it's pretty simple. So it's 4 lines. So I'll just go through it. So since A is less than B, so this is for one median now. So before I said, okay, we want it for every clusters, but K is 1 here. So basically, I'm just saying that A is less than B now. Since that's true, there's some injective map from A to B, because B is bigger. So just pick any injective map. It doesn't matter which one. And let C be, so I should specify lowercase c, let that be the optimal median for A union B. And let S be the optimal median for B union C. So you can think of your stream like this. So first in your stream you get A, then you get B, and then you get C. So I'm saying if I want to cluster A union B, C is the optimal center. And if I want to just cluster B union C, S is the optimal center. So just with this, what is the sum of, so this is just kind of like a mini lemma. I want to bound the sum of connecting A to just passing through this injective map from A to B. So connecting A to its representative in B. So by the triangle inequality, I'll just pass that through the point C, the center. And this is, of course, less than the cost of OPT A union B, because here I'm saying connecting all the things of A to the center, and connecting all the representatives to the center, but all the representatives are going to be some subset of B. So if I connect them all, that's even bigger. So it's OPT A union B, which I've, by assumption, is going to be less than alpha OPT of B. So the second of the 4 lines is, now let's bound these representatives connecting to S, the optimal center for B union C. And again, this is just a subset of all of B, so it's upper bounded by that. And of course, I'm just connecting B, so that's less than if I had connected B and C. So that's less than OPT of B union C. So just to put these together, I can break connecting A to S as these 2 terms, which I've already bounded above, so I'm just plugging in. So it's 1 plus alpha, OPT of B union C. And then I have my result, because now OPT of all of them, I break it up into the A, and I break it up into the B union C. And these are just my result, the previous line from before. So this was done for 1 median. So if kind of like a visual for, you know, what did we do here? Just imagine that the blue is A, and the orange is B, and the red is C. So so in particular, A and B have the same size here, but in general, B can be bigger. So pick some injective map. So I'm sending this point to this point, and this bottom point to this bottom point. That's my injective map. What's my optimum center for A union B? This is going to be my optimum center right here in the center, and my optimum center for B union C is right here. So everything on the previous slide basically just made this simple observation. If I want to connect all the points in A to this center here, so I just want to bound, all I need to do is bound this cost of connecting A to the new center. So all I'm saying is I can pass through, first I can pass through G of A, its representative. So instead of going straight down, I can go to B and then down. And then from going from A to B, I can pass through this optimal center. So basically, if you see the change to the color blue there, basically first I go down to the center, then out. And since there's more terms in B, this is upper bounded by the OPT there. And the second part is upper bounded by OPT B union C. So this is for the 1 median case. I have this bound. And the K median case is basically just, we need some way to keep track of the cluster sizes, which I'll show later. But given this fact that they all satisfy the property, it's just repeating this proof K times. It generalizes. So how can we build a histogram using this lemma? So if these hypotheses can always be satisfied by some chain of polylog prefixes, so what does this picture mean? If you're familiar with the smooth histograms, each one of these bars is an insertion-only instance. I just started a regular streaming algorithm. And so here, oops. This is like my oldest point, then my next oldest point, and we keep going, and here are my more recent points. So this is some algorithm I started a long time ago that only accepts points. It's not a sliding windows algorithm. It's just accepting points. And then I do that every so often to keep this histogram. So if I can always satisfy these conditions by a chain of polylog and prefixes, that's just for my space requirement. I don't need that except to bound the space. And if I can check whether 2 prefixes satisfy this in polylog space, then I'm done. So how do I use this? Well, if, let's say, if every adjacent one satisfies this lemma, so I'm saying at some point this one and this one had similar cost, and they had this cluster size relation, therefore, by the lemma, they will always have similar cost. Well, let's say that my window right now falls, okay, so if I get lucky and my window falls exactly here, I can just use this algorithm, this output exactly. But let's say my window falls between these 2. So I know that this guy is bigger and I know that this guy is smaller, but I actually just want a solution for neither of them, something in the center. Well, since I said that I'm guaranteed by the lemma that they're always remaining similar. So I'll just use the bigger one for clustering. But by the lemma, this is going to give me a good clustering for the window, which I don't even know what the full window is because I've deleted some of it. But because they're guaranteed to be similar, I use the superset to approximate the current window at all times. So if these two things are polylog space, then we have an algorithm. So kind of the basic case, just keep two segments, A and B. So there's this Pls algorithm, which does the following. So I'm going to run it on each segment separately. So Pls, you keep an input of n points. So say these blue points and the red points, everything. And what it does is it runs a facility location, kind of in exponential estimates for what the cost will be. But that's kind of how it works. But the end result, which is important, is the following. Using it basically compresses endpoints to k log squared endpoints, where the weight of each point is just the weight of the points that it serves. So by compresses, what I mean is we started out with the blue, but now we just get the red, which is polylog size. And by the weights, we actually have enough information that we need for clustering. And the essential property, again, is that all these connection costs are a constant times OPT. So just a visual for how it works. We start with the endpoints. We run this Pls algorithm. The algorithm is this arrow here. It gives you k-log, okay, so k-log squared endpoints. And then you run an offline approximation, and you can get k points, a constant number of points. So how do we do this? Run it separately on A and B. So we have these two facility sets, one on each one. And then find, so this is not a typo. I actually mean here just on A. So I have Pls of A union Pls of B. So I have these two facility sets, and find a constant approximation for them. And then I can have these two maps from A to its facility set, and then to the centers, not for A, but actually for A union B. By the weight, I said the Pls set gives you weighted points. So just by the weight of the point, you know how many original points were connected to it. And then we actually have this set in memory and this set in memory. So we can go backwards. For every center C, we can jump to PLSA to see how many points were connected to it, and then we can jump back to A by adding the weight. So now when we have the clustering, doing this trick actually tells us how many points in A are connected to this cluster, and likewise for B. It tells us how many points in B. So now just using k log squared n space, we know exactly what the two cluster sizes are. So we did this for A and B. So here in this picture, let A be like this. Here are two adjacent ones, this bottom at the red and the top of the blue. So let A be kind of the difference between them, the part that's in the top but not the bottom, and let B be the rest of it. So we run it for those two separate, and just do this for each prefix. So if I have t different instances, I need to do it between each pair. So I get order of t squared. So I want to do this between each one. And how many bars will I have in total? Well, what were my two conditions I needed to satisfy for smoothness? OPT was similar, and then all of the cluster sizes were similar. It didn't drop by a factor of 2, basically, because I wanted A to be less than B for each cluster. So the drop in OPT can occur at most log n times. Not really, but that's our assumption, polylog n, that OPT is polynomial in n. Because if it isn't, then, well, I shouldn't say a linear space lower bound. We have a super polylog space lower bound. And in general, if you have some kind of like exponentially decreasing series as your points, you'll need to use linear space. But this is kind of a pathological thing. So even the previous paper in polynomial space, they need to make this assumption, because otherwise you can't do anything if you have an OPT that's like growing exponentially. There's nothing you can do, or rather decreasing exponentially. So this, we're saying, occurs log n times. And dropping cluster size, well, each cluster can drop by a factor of 2 at most log n times. And there's k clusters. So altogether, a dropping cluster size can occur k log n times for each of the k clusters. So altogether, we have k log squared n bars on our graph. Okay? And we delete all the other ones. so each one takes k log squared n space, and I said we do it for each pair, so we square it. So in the end, that's where the k cubed log to the 6th n is. And basically every time we get a new point, we start a new bar, a new instance, and we keep doing that, and then every now and then we check to see, are these conditions satisfied by any bars that are not adjacent, further away? Because if they are, we can delete all the ones in between them. Because after 2 bars satisfy the condition, they're similar, we can delete everything in between. So that's how we maintain the number of segments to be order of k log squared n. And that's it. I have some open questions later after.